The reason I propose this talk is because being able to query your index is something that your users, of course, are constantly doing, but being able to richly interpret those queries and give the best results back to your users is an extremely important aspect here. And so we're going to cover, it's primarily Solr focused. Of course, the underlying queries that are issued are at the Lucene level, but it's primarily Solr focused here for what we're talking about. There's a lot of query parsing capabilities in Solr, and I think it's underutilized in terms of the rich capabilities that are there within the built-in features, as well as the ways that you can extend the system to plug in your own implementations. So this is basically just a copy and paste of the query parsers that are available in Solr. These are the built-in implementations. A little bit more human readable. I changed it over to use the actual strings there. Those strings that you see on the left are the actual names of the query parsers that you specify when you are selecting which query parser to use. The default query parser out of the box with Solr is called the Lucene query parser. It's called the Lucene query parser because it uses the Lucene syntax, but it actually extends, and we'll see the details of how it extends the Lucene query parser itself. And as you can see, there's a number of other query parsers there. Again, it's very pluggable, so you can add your own query parser implementations when you need to get to that point. So let's first talk about the default query parser, the Lucene query parser. Again, it's a Solr extension of the Lucene query parser. It adds field type awareness so that the terms are interpreted with the knowledge of the field type in terms of its internal representation in the index. So things like numerics and dates, those things will be turned into their underlying implementation, the representation that gets indexed based, again, off the field type. Some other fancy things that it supports is the date math capability, so that you could say today minus 5 months, that sort of thing, when you're doing range queries and so on with dates. There's a feature in there for reverse wildcards. So if you're searching for foo star, if you've used that reverse wildcard filter during indexing, the field type knows that, and the Lucene, the Solr extension of the Lucene query parser will recognize that the terms were reversed during indexing, and will reverse the terms also for the wildcard queries for increased performance. There's a couple of magic fields that the Solr's Lucene query parser adds. Internally, they're actually even called magic fields. There's the underscore val underscore. That allows you to plug in a function query to add to the score during scoring process there. And then there's this special one called underscore query underscore, and we'll talk more about that when we talk about the nested query capability, where you can, it's basically a portal into leveraging other query parsers within a richer expression. And here's a new feature that actually is a really nice capability in terms of when you're dealing with prefix, wildcard, and regular expression query terms. It's long been an issue that if you've indexed your text and generally use a lowercase filter for indexing, if someone searches for a capital letter with a star at the end of the expression, capital F foo star, that you won't get any matches. And that is because the capital foo star is not analyzed. It doesn't go through any analysis process in the default Lucene query parser. And that's actually simply because it's a things like stemming and other operations don't make sense when you have a partial term and you're trying to do that sort of thing. However, Solr adds a special type of analysis, and again, this is a relatively new feature, to allow you to specify a light analysis chain. For example, simply just lowercasing often is all you need for these types of expressions. And you can specify that by creating a new analyzer definition for a particular field type and give it type equals multi-term. Even without specifying type equals multi-term, you can benefit from this capability because it automatically will create a multi-term analysis chain based on the query time analyzer, and any of the tokenizers, character filters, tokenizers, and token filters that implement an interface called multi-term aware component it will automatically build up a chain of those. And if none of them are multi-term aware components, then it will simply use the keyword tokenizer, which is exactly the same behavior as before, where there's no analysis done at all. So that's a really nice addition to this Solr's Lucene query parser. Next up is perhaps a query parser that many of us are familiar with. It's called the Dismax query parser. The Dismax query parser supports a constrained set of syntax. So basically the syntax that you see there, where you can put phrases within double quotes, you can use the plus and minus operators for required and prohibited terms. And then you simply, of course, can use just loose terms in the expression as well. And that is all of the syntax that the Dismax query parser supports. And this is because it's designed for user input, where users are not considered and are not necessarily power users and know all of the fancy syntax that the Lucene query parser supports, which actually can get you in trouble when you put in special characters that would cause parse exceptions. So the Dismax query parser is a nice one for user input, and one of the benefits that you get out of the Dismax query parser is being able to individually control the boosts for scoring across multiple fields. There's a query fields parameter, QF parameter, where you specify you want to boost the title by 5 times and then simply use the body with a normal 1.0 boost. And then when the query terms are spread across those fields, matches in the title field, for example, will cause those documents to rank higher. And that's typically the effect that you want when you have rich documents with title and body and those types of fields there. There's a number of bells and whistles, parameters and knobs and dials and stuff that you can tune with the Dismax, and then again on another query parser, the extended Dismax. Many parameters here. You can also specify phrase fields. It will take the expression, the query expression, and construct a phrase query, and optionally add that into the Boolean query that gets generated under the covers. Allowing if the entire set of terms matched a particular document within some proximity, and there's implicit phrase swap that you can provide there, so that the proximity, as long as those terms are within a certain proximity, those documents will bubble up higher. There is a sophisticated parameter called minimum match. This takes, it can take a simple number as a parameter, the number of terms that must match. It can also take a percentage, so 50% of the terms the user provided must match. And it can also take an expression that provides the number that must match depending on the number of terms in the clause. So you can say if there's 2 terms in the expression, then 50% must match. If there's 5 terms, then 3 of them must match. And if there's 6 terms, then 75% of them must match. So you can specify that type of gradient across the number of terms given a MM expression there. And that effectively gives you a gradient between and or. So not all terms are required, and it's not an or across all of them, which gives you too many matches. As well as that type of matching capability that you have in terms of boosting, there are two parameters that you can control there. There's a boosting query and a boosting function, and you can provide n number of these expressions there, and they are additive boosts into the score. So you could, for example, boost, and we had this question in the last talk, the more recent documents. It's a very common boost query that's provided. It's even documented like that on the Dismax documentation as an example, is how to boost more recent documents. So you can take the last modified date of a document and provide a boosting function so that more recent documents get a higher weight there. In terms of debugging, and I'll talk about debugging towards the end of the talk as well, because it's very important to be able to troubleshoot the queries that Solr generates, just to have insight into what happens. The Dismax also provides debugging output for the boosting and function queries. So you can get some deep troubleshooting information there. Okay, so we've just seen two different query parsers. Probably the two most popular query parsers that in use in Solr today. How do you switch between those query parsers? How do you select which one to use? There is a parameter that you can provide either in your request to Solr or within your request handler definition as a default or as an invariant. And you can say that def type, the default query parser name basically, and say what the name of that query parser is. And again, the default one is literally Lucene there. And in order to understand all of the other examples that we're going to see here, I wanted to provide this syntax here for different ways that you can specify the query parser. You can use this curly bracket bang syntax here where you can say parser name and then provide what's called local parameters within that curly bracket expression, and then provide an expression after the closing curly bracket to select a query parser, provide local parameters for it, and the expression all in one shot this way. And that's instead of using or to override what the def type value is there. This is a very handy syntax to be able to use when you're doing filter queries, for example, where the default query parser for the filter queries, and in fact in all other places besides the main query, the default query parser is the Lucene query parser. And so you need a mechanism to be able to locally override the query parser being used if you need to provide a different one. And we'll see some cases where it's actually recommended to do this type of thing. Not only can you provide the expression outside of the curly brackets, there's another parameter just simply called v for value that you can provide, and you can see that last example there. So all three of these examples right here are equivalent, and we'll see cases where actually using that v syntax will be important when we start getting to nested queries and so on. Okay, so this will be a good reference here for the mechanisms for specifying the query parser. So given that we now know how to specify a query parser, I want to provide kind of a clever example here of using a request handler mapping as well as the curly bracket syntax for overriding the query parser. So I've provided a /document request handler here, and I've made the parameters, some parameters here invariant. So I've defined the main query as a term query, and we'll see what the term query does in just a second, but if you know Lucene, it's simply a term query. And I've told it I want to use the field ID, so that's the F parameter and the V parameter are built-in capabilities of the term query parser. And I've said that I want the value, the V parameter here, to be $ID. This is local parameter substitution, being able to indirect a parameter from a request parameter, or it could also be a parameter that's defined in the request handler itself. I've made those two, and I made that invariant. I've also said rows equal 1 as an invariant because my request handler here is designed simply to return back a single document. And if with this term query and you're actually doing the ID field, if that's your unique key, there would be no way to return back more than that in this case. But I just put that in there explicitly to show that. And actually, just for completeness, I trimmed down the search components that are being used in that request because when you're retrieving a document, you don't need faceting, you don't need spell checking, that sort of stuff on there. But I did put the highlighting in there. Perhaps you want to provide a hl.q parameter for the highlighting and actually highlight fields in that document as you render just that single document. So I kind of did that just as an example to show not only query parser, but how you can do some interesting things with a request handler definition. So we've seen this local parameter syntax. We've seen the Lucene query parser has this backdoor underscore query underscore magic field. Now I can show you how to combine those things to have what Solr calls nested queries, but it's a way to use the Lucene query parser and you then leverage that underscore query thing to parse various expressions and combine, in this case, multiple Dismax expressions into a single ultimate query to execute here. And in this particular case here, I'm using the Dismax. The first Dismax there is going across the title field with a boost on the title and then the body field as well. And I'm using a $user query, and this is an arbitrary parameter that I've provided, defined here, and then later, either in the request, again, in this case, it'll be from the request, or it could be from the request handler mapping, provide a value for that user query parameter. And then I use Lucene's query parser syntax and that with another underscore query underscore expression where I'm dismaxing a topic parameter across the keywords and the description field. In this case, the example I'm using here, I actually set up a crawler to crawl Bundesliga.com, and I searched for the Hoffenheim-Schalke query here. This is local information. I went to the game on Saturday where Hoffenheim did a great job beating Schalke. And so as you can see here, the next two lines are I'm providing the user query and the topic. If we leveraged that last example where I hard-coded the actual queue parameter in the request handler mapping, now my search client doesn't have to have this kind of ugly expression being sent from the search client over. It can be hard-coded into a request handler definition, and the only thing the client needs to provide are those blanks to fill in, that user query in this example and the topic. So that top queue thing, again, could just not be something that is sent by the search client. It's just hard-coded in the definition of the request handler. As a real-world example here, in the library world, they have a very complex set of data where, for example, we think of books have a title. Well, books really have a title and a subtitle, an alternative title, and like probably 10 other types of fields that represent the title. Librarians want to be very nuanced and be able to search any of those various things that we all kind of think of as a title. And an example here is Stanford's University Library website, SearchWorks, there, where they have, I said, insanely complex set of these Dismax things. Basically, this expression up here, except with a lot of QF parameters, a lot of PF parameters, and that sort of thing. And you can also, and I mentioned this on the previous bullet point there, indirect the QF and PF parameters. Any parameter, any of those local parameters, you can indirect with that $ indirection there, the substitution. So some very clever tricks that you can pull off by mastering these types of capabilities here. Okay, so we took a break there between those two query parsers to show how we can leverage these things. So now we're going to go back and talk about several other query parsers that are available. There's the extended Dismax query parser. This is a superset of the Dismax. It combines the Dismax capabilities with the Lucene query parser capabilities so that you can actually use Lucene query parser syntax as well as the Dismax capabilities. In a recent development, and I think Jan is actually here somewhere, he added this user field capability so that the extended Dismax can even restrict the fields that can be queried. So this is a nice capability because one issue with opening up the Lucene query parser to your end users is now they are able to query on fields that you maybe thought were private, that you didn't really surface in a way that they could easily query, but if they knew the field name, that they could query on that. So if you have like your profit margin as a field there and you're using that for boosting, then they could perhaps query on that. So you can actually restrict the fields that can be queried with the Lucene syntax with this. So this is a very nice trick in there. And one really pleasant piece about that user field parameter is that you can use wildcards in there. So if you have dynamic fields, or you just want to say star here, accept all fields except cost and timestamp, for example, right here. The extended Dismax has several other powerful capabilities in there in terms of relevancy here with the shingling of the terms. So you can take, you can specify a PF2 and a PF3, phrase fields 2 and 3, and it will shingle the query into 2 term chunks and 3 term chunk windows across the query expression, and optionally or them basically into the ultimate query so that they provide a boost when they match. And in this case, with the Dismax, literally the entire query expression is treated, if you use the PF parameter, is treated as a single phrase. And if you're using the Dismax for what it's really good at, spreading across title and body and keywords and description and other fields like that with various boosts, if a user puts in terms that are in various fields, a phrase field doesn't really help because that single phrase is not going to match on any single document because they're spread across multiple fields. With this PF2 and PF3, you have a much better chance of catching 2 and 3 word combinations that may appear in individual fields, and the relevancy will be drastically improved when those types of matches occur. So that's a really nice feature in the extended Dismax there. Also, stop words get removed from the single phrase queries because it's just a nice way to bring those things in and make sure that they count when needed. An improvement, well, it's actually a feature on top of the Dismax. The extended Dismax also supports the BF and BQ parameters, the boosting function and boosting query parameters that are additive to the score. However, adding to the score is often not good enough. You need to actually multiply something into the score, and you simply can't do that with the Dismax. So there is now a boost parameter with the extended Dismax, and allows you to multiply numeric factors into the score. So that's something that's drastically needed in some environments. And then there's a few other, and as I was creating these slides, I was referring to the extended Dismax wiki page, and then of course the source code as well. And I discovered a few other parameters that actually aren't documented, but they're in the source code. And there's the stop words parameter and a lowercase operators parameter there that you can leverage. So if you indexed stop words, but you want them included or excluded, you can control that in the phrase that it generates. And then you can also allow, and in fact the default for lowercase operators is true, but you can make it so that you require capital or and capital and. Okay, so that's extended Dismax, a really handy parser. In fact, this may be the parser that you want to use for your user queries moving forward, simply because it is Dismax, but it has these additional capabilities. Again, just be careful with because it does support the Lucene syntax, that you're aware that users could drill into particular or query on particular fields that you may not think that they could have. So. But it's a very powerful parser. Good stuff there. Okay, so let's go from the most complicated parser in Solr down to perhaps well, not quite the simplest. Well, the raw parser that's mentioned here is the term query parser. The term query parser simply creates a Lucene term query. The Lucene term query is the most atomic query available in all of Lucene. We saw in that previous presentation where the inverted index structure, what that looks like. You simply want to say this word now match all the documents that have that word in it. The term query parser is field type aware. So what it will do is know that a particular field is numeric, and it'll know the type of numeric that it is, and it will convert the value into the internal representation and match. Same with dates, and so on. So it knows about the field type, whereas there is actually a raw query parser. I just kind of use that as a simple bullet point here instead of a separate slide, because very rarely would you ever need to use the raw query parser at this point. But the term query parser is handy because of its field type awareness. In terms of when is a good time to use this term query parser, if you are rendering facets, which pretty much all of our applications now are rendering, when a user clicks on one of those facets, what you typically do is add an FQ parameter to your next request to Solr for a filter query. If you simply and naively use the filter query parameter and say the field name that they clicked on and the value that they clicked on and put that together as a Lucene query and said FQ equals field name colon value, if you have very simple text that doesn't have any special characters in it, great, it'll work fine. However, if you have values in there that that are special characters, for example, then you can come up with issues. And some people have solved this by doing FQ equals field name colon and then put the value inside of double quotes. That works great too if the special characters aren't a double quote, right? So, and you can get even crazier and start escaping things. You can backslash escape things inside of that expression, and that will all work fine. But if you want to simplify your client so that you don't need this escaping madness, then you can simply use this term query parser, where you simply say FQ equals term equals F equals the facet field name, and then close the curly brackets, and then put whatever crazy value there happens to be with double quotes, with whatever, no escaping necessary. I made a note here. Yes, you do need, of course, to URL encode the parameters, but you won't need to do any backslash escaping or anything. It will take that exact value and use the field type awareness, which often is strings, so there's no, it's literally the raw value anyway, and create a term query, and you're safe from all the escaping and query parser madness that might be there. For completeness here, we'll talk about a few more of the query parsers. This one probably is pretty niche. I'm not really sure when or why you'd need to use this in practice, but I'll just mention what it does here. This creates a prefix query, very much like doing value star in a Lucene query syntax, where it's literally a prefix query in Lucene's API. Let's see. Yeah, as I mentioned before, that multi-term awareness that the Lucene query parser has, this prefix query parser doesn't have that. It probably we probably should consider putting that type of thing in there, but and put some field type awareness here. But at the moment, there's no field type awareness. It is what it is. It's the raw value as a prefix there. There is a boost query parser. The boost query parser is what gets leveraged by the extended Dismax query parser when you use that boost parameter. It wraps another query and provides a multiplicative boost to the scores that the original query that you're wrapping produces. And so here's an example basically of doing date boosting. So more recent documents get boosted. There is a field query parser. This is similar to the term query parser, except that it actually runs through the analysis process, and depending on the output of that analysis process will generate a different type of query. So if only a single token comes out of the analysis process, then you have a simple term query. If multiple tokens come out, it depends on whether those tokens share positions or not, depending on, and that will affect which type of query gets generated. And certain field types handle fielded queries specially. There's a special method on the field type that says get field query. And things like currency and the spatial types, they have a special implementation. So if you had exact points that you wanted to query on, for example, location here, you can do this type of lat long if that's the type of field type that you're using for the location field here, then you could leverage the field query parser in this manner. Now this would be an exact, this isn't a bounding box or any kind of thing, it's an exact point that you must have indexed here. This is a relatively new query parser as well. I am practically certain this was a 4.0 only query parser. This one is an interesting one. It allows, it generates what's called span queries in Lucene's API. And these span queries allow you to do very minute matching of positional things that are within a certain distance, either ordered or unordered, and you can combine that with wildcards and regular, I don't think you can do regular expressions in here yet. That would be a nice one to add, actually. Wildcards and prefix queries and fielded queries. Okay, so no phrase queries. Phrase queries basically are implicit because you can say this term within one of another term in an ordered manner. And so you have these operators where you can say W or N and provide the value of the proximity there, and provide so it will generate very rich queries here for proximity. There are a few caveats to this thing. The query parser, and this was an intentional design decision by the creator of it, does not do any analysis of the tokens there. So this is different than our typical query parsers such as the Lucene and Dismax, extended Dismax, where user provides query, it's going to run through our query time analyzer to make sure that the terms get lowercase and stemmed and so on. This one does not do that. And the reason, the design decision here was that you're trying to find things with prefixes very often. So you'll basically create everything lowercased in the query, and you'll use star at the end of partial terms to be able to get these proximity matches. So there's no analysis of that. So that's a pretty important caveat there to be aware of. And this may be, well, it's not quite the last query parser we're going to talk about, but the join query parser. This is effectively a pseudo join where you can specify a from field and the query, and it will make that query and pull all the values from that from field and match that to a to field and match the documents that from that to field that match that inner query, basically. So it's similar to a SQL join, but not quite in terms of the final result includes the two documents with no information from the from documents all, including the score or any of the field values, anything like that. Literally, the documents that you get back are in the two, and that's it. A very powerful thing that you can do here is join across cores, local cores. So as long as you have the core within the same Solr instance, you can join across that. So that can be a very handy way to do things like have security information indexed into one core and your documents with the user IDs attached to that core with this join query, and the access information is something that may change more rapidly so that you can achieve better commit times and so on, warming times, by having things in a separate core. And there's other examples of where you could leverage this type of thing. And you can let your imagination kind of run wild with this. There are some certainly some scalability concerns there, so don't think that you can now completely denormalize your model and create it in all separate cores and leverage this join thing like you would a SQL database. Okay, your first way to design your system should be to think that you're going to flatten your entire world into documents with fields on them. Only when this design fits with the join capabilities should you start leveraging this type of thing. There's spatial queries here. There's a geohash, lat long, and point types. With those particular field types, you can leverage a geofilt query, which is exact distance matching. And then there's a bounding box, which takes the corners and creates a box. So you may get more documents than match the distance that you want there. But it's a much quicker type of query and might be just plenty good enough for your needs there. And often when you're leveraging this type of thing, and this was a question that came up in the earlier talk as well, was about geodistance stuff. With Solr, you can leverage this geodist function to be able to sort by that distance. So find pizza near me and order it by the closest one. And then, of course, you could also toss in rankings by recommendations and ratings of restaurants and all that sort of thing into the equation as well. You can return that distance as well using the new feature in Solr 4 called these pseudo fields, where I can use the field list parameter here, FL equals, and give it a field name colon, a pseudo field name, colon, and then some function, and it will create the value of that function and put it inside of the document structure that gets returned to our client. Frange query parser. This one allows you to do term, range, textual or numeric actually, and Yannick actually has written up some interesting stuff about being able to leverage textual ranges there and the performance benefits that you can get with textual ranges. But probably primarily you're going to be leveraging numeric type ranges on these things, and then you can provide a function or simply a numeric field value and do a range over top of that. The nice thing about this frange, as well as this other infrastructure called a PostFilter inside of Solr, and this is kind of a niche feature, but when you need it, you really need this type of performance benefit here. When you apply queries and filters, these types of things get cached. The sets of the documents that match a query, the sets of the documents that match a filter become cached as document sets, basically, and intersected to come up with your final result. Being able to generate a document set and cache that thing when you're talking about something like access control can be extremely prohibitive. It's going to change basically every time you do a query, so caching it doesn't really help, but it's very expensive to generate that type of thing. So Solr has implemented this thing called a PostFilter. It allows a last chance callback mechanism so that documents that have made it through the query and filter process, all of the other cache stuff that makes a lot of sense to cache, can now be vetted at the very last second before any other processing occurs to ask if this document should be included in the results. So after the result set's been narrowed down, you can call back and say, does the user have permission to view this document, and do it just for the documents that match everything else. And there's a few tricks to enable this. There's a few queries that implement this out of the box. There's the frange, then the geo filt, and the bounding box query parsers support this. And you can write your own custom ones as well. And so there's a couple of blog entries down here, one that Yannick wrote, one that I wrote, that explain this stuff in gorier detail. This is really talking about how do we handle queries that where we want to be a bit looser. We want to include some phonetic information, sounds like type things. We want to include stemming. We want to include synonyms, but we don't necessarily want to include those features in a direct manner. We want to be able to boost things that match more exactly than with these other capabilities turned on. So one of the things that you can do is copy field your text into another field where you turn on the phonetic filter or you turn on stemming, and then you can use the Dismax, as you see as bottom example here, where we Dismax across the original field and then a phonetic field, and we boost the exact matches higher. And interestingly enough, that particular query, when you run it through the double metaphone, or run that text, and I don't even know how to pronounce it, I'm not even going to try, that particular query there, it generates exactly the same phonetic as the word Munich. So that's why I use that example there. Here, I want to leave with a few points here about how you model things, especially when we're talking about suggest, because as we're talking about query parsing, these days we're more and more talking about suggesting things as the user is typing. I've got this title, Things Not Strings. There was an interesting Google blog post about how they're doing more semantic web and knowledge-based things, where what you want to present to the user are objects, not just strings there. And so one of the things that people try to do when they have a very rich domain, they try to leverage Solr's suggest capabilities, and they're fantastic. The new stuff is great. There's some really nice performance benefits in the new auto suggest capabilities there. But there's a limit to where that really makes sense, because now you're going to have to start changing your analysis to facilitate this suggest capabilities. And if you're indexing parts, as my first example here, car parts, and when the user types, what you really need to be able to suggest them is the actual vehicle, a year, make, and model of a vehicle. And in this case, it can, and I put better with a question mark because it always depends on what's better. You really have to figure out what's right for your domain. But it can be better to model those vehicles as a separate complete index or a separate document types within the same index, and leverage Lucene, Solr's search capabilities, and rather than suggesting field values, you're suggesting documents, and you're doing real searches against a real index. And bringing back documents where you can weight things by fields and do all of the rich query parsing things that we've already been talking about. So consider that sort of thing here with your domain, whether it makes a lot of sense to model it as a separate documents or as trying to suggest out of a field term value. Okay, so just finally some query parsing troubleshooting tips. There's some pretty neat capabilities here with the analysis request handlers. There is a field analysis request handler. This thing is very interesting, where I can provide a field name, a field value, and then I can actually say show match equals true, do a query for ApacheCon here, and you can see that there is a Boolean value that's returned that says it's a match. So you could actually leverage this sort of thing to figure out where people's terms match within a document field, and maybe this is something that you could leverage during suggest capabilities as well. So keep this in mind, that you can leverage Lucene's analysis stuff even without indexing things. You can have a field type defined, pass in values, and get back what the analysis would be had I indexed the document. And so in this case, maybe that's a query there, and we're seeing where a particular query matched on a field value there. There's two debugging capabilities that are worth noting here. The query parsing debugging, and this is Solr 4's new debug parameter. You can say debug query equals true as always, but you can also fine tune it and just get back the query parsing if you want, or just get back the score explanations. And both of those are very useful when you're tinkering with query parsing to figure out what query got generated, and then why did that query score the way that it did for particular documents. Like one more minute here. A few things I wanted to point out as coming at some point in the future to Solr. These top two are issues that I opened that I have been a bit lazy on actually completing, but there's a XML query parser capability at the Lucene level. Now, it may seem a little ugly to think of, of course your users aren't going to type in an XML query and send it over the wire. But the XML structure is really a tree structure for the query, and it allows for placeholders so that you can inject, for example, advanced search type things where title and author and other types of fields you may want to inject into a tree structure, into a rich predefined query tree. So that XML query parser has a lot of potential there. Especially at the Solr level, where we add in field type awareness and that sort of stuff, and query substitution. The previous presenter talked about payloads. You can actually put payloads on terms with Solr, but there's really no way that you can query and use those payloads there. So that's to do. And then of course we'll see Martin's next talk here. I'm probably eating into his time for a second, to talk about the block join stuff. That's a to do for Solr as well. And that's the end of my talk. Sorry I didn't allow time for questions. I know Martin needs to get up here and present straight away. But I'll be around, so feel free to ask me questions over the course of the day. Thanks.